In last lesson, we presented the first machine learning model, a supervised model called linear regression. Today we will extend the regression with a more powerful method called polynomial regression, and then we will start looking at classification. In particular, I will first define what is a polynomial regression. Then we will see one of the most important trade-offs in machine learning, that is variance versus bias. And we will see how to avoid too much variance, also called overfit, in our model by using regularization techniques. We will see why it is important to scale features before training models, and how to select features, the most important features for your model. Then we will go to classification, and in particular I will give one of the simplest models for classification called logistic regression. Then we will explain the metrics to evaluate the performance of classifiers and how to deal with class imbalance. So let's start with polynomial regression. What is a polynomial regression? Well, let me change the scene. A polynomial regression is a univariate polynomial regression, so we are looking here at just one feature, this x, is a model that looks like this one. So you have just one feature, okay, but then you also add artificial features, let's say, that are just the square, the same feature to the power of 3 or 4 up to a polynomial degree p. So if p is equal to 2, we say the model is quadratic. If is equal to 3, this is incorrect, the model is cubic, etc. So every time you add an artificial feature, you also add a parameter that goes with. So the larger the polynomial degree p, the more complex is your model, because you have more parameters. Observe anyways that at the end, a polynomial regression is nothing more than a linear regression where you have just more features. But you can compute these parameters theta 0, theta 1, theta 2 by using ordinary least squares, as we presented before. P is a hyperparameter. It means is a configuration parameter of your model, and it's up to you to choose the right one, and we will see some ways to do it. So this is a univariate polynomial regression where we have just one original feature. Let's see how a multivariate polynomial regression looks like. So we have first the original features, then we have all the features to the power of 2. Then if our polynomial degree is more than 2, we will have all the features raised to the power of 3, etc. And then we have all the combinations of features. Here we are looking at the quadratic model, so we have all the combinations of two variables. But if we had, for example, a cubic model, we had to include all the combinations of 2 variables and also of 3 variables. Okay, so you see that already with a small degree, your model starts to become very complex, in particular if you have a multivariate polynomial regression. How to choose the right hyperparameter p, the polynomial degree? Well, the right way is to use cross-validation. So first, as usual, we divide our data set in a training set and a test set, and we forget about the test set. Then we perform cross-validation into the training set. So we divide it into k folds or slices, and we select these slice as our temporary test set, and all the others are the training set. We train the model on the training set and we measure the performance on the test set. And we put this error aside. Then we choose the second fold as a temporary test set, and we use the other 1, 2, 3, 4, 5 folds as training set. So we train the model on the training on these 1, 2, 3, 4, 5 sets, and we measure the performance on the temporary test set, and we keep this value aside. And we do like this 1, 2, 3, 4, 5, 6 times. Okay, and then we finally measure the average error. We repeat this process for all the values of polynomial degree p. So at the end we will have an error, an average error, a cross-validation error for the polynomial degree p equal 1, an error for the polynomial degree equal 2, etc. And we will and each error is a cross-validation error. Okay, and we will choose the p which gives us the smallest cross-validation error. Suppose this is p equal to 5, let's say. Then we will take this model with p equals 5 and we will train it again on the training set, and we will test it on the test set. Okay, so observe that it is very important to put the test set aside, because if you include the test set during your measures to choose the right hyperparameters, you will not have a realistic evaluation of your model, because then in reality you cannot know the test set, the new samples, to choose the right hyperparameters. So you only use the training set to do cross-validation to choose the best hyperparameter, and at the end, once you have selected the final model, you measure its performance, its error on the test set. So let's see how can we code the polynomial regression in Python. So the first Python notebook of the lesson is called Polynomial Regression, as you can guess. And as usual, we start by importing some libraries, by downloading the datasets. And first, so just to change a bit the scenario, this time we want to predict the buffer health. That is the number of seconds that the video clients of the users have already downloaded. So they are already in the video client, already there to be reproduced. Of course, the more the buffer health, the more the seconds we have already in our video client, the better, because our video client is ready to reproduce video chunks. If instead our buffer is empty, our video client is just stuck. It cannot reproduce anything, and the user cannot see the video just stops. So the more the buffer health, the better. So we want to predict this by just looking at network information. So we imagine that a network operator wants to measure the traffic and understand if there are some clients that are having a too small buffer. So in this case, they can try to favor these clients in order to avoid loss of quality of experience. So we first start by representing our datasets. We just consider one feature for the moment, bytes received, and this is what we get. We also represent the same dataset by using this time a logarithmic transformation of bytes received that we have already computed in other notebooks. Here we just reuse these features that we have computed before. This is what the dataset, the transformed dataset, looks like. And okay, here I put in red the test set and in gray the training dataset. Let's start to train a linear model, simple linear model. So we do it on the training set. Where is it? We doing on the training set, and we test as usual on the test set. Model predict. These are the predicted buffer health values, and we print our model. This is our linear model. Now let's try instead to run a polynomial regression of degree 2, so a quadratic regression. So first we just construct the artificial features. That is, with this function we just give as input x1, that is kilobytes, bytes received log, and as output this function gives x1 and x1 squared, a vector composed like this. Okay, so in x-train poly we have just this. So now we can simply run a linear regression that we've already seen on these pair of features. So what I want to say is that polynomial regression is just, at the end of the day, a linear regression with more features. So here I'm creating a linear regression as before, and I'm giving as training set train poly, that is the one with the feature and the feature squared. And as usual we plot it. Okay, this is the line we obtain, and we check the test error. And we observe that we improved a bit, like 0.3 seconds of precision we gained. Now let's do the same with cubic regression, and this is what we get, this green line. And you start to see already that this line is a bit too twisted. And observe that if we measure the error on the training set, we have improved with respect to the quadratic regression. We have improved a bit. However, if we then compute the error on the test set, we are going worse than the quadratic regression. This is a clear example of overfit, because our model is twisting too much to adapt to the training dataset, but then it is not generalizing, because then when a new sample comes, the test set samples, its performance is really bad. Let's exaggerate and let's try with degree 25. This is the line that we get, the gray line. And of course this is not realistic, it's too twisted. It is trying to adapt to every single gray point, to every single training point. So again, when we increase too much the complexity, we are not generalizing enough. This is just a code suggestion to use pipelines. So observe that every time we wanted to run a new polynomial regression, we had always to first transform the features in order to add the higher degrees, and then train a linear model on these transformed features. Okay, and we have to do it for training, and then we have to do similar things for testing. Instead of repeating always the same code, we can use pipelines. Here we are constructing a pipeline that is composed first of this polynomial transformation and then of a linear model. So actually a pipeline is something like, let me close this. A pipeline is an object in which you can put many modules. In this case, so this is the input, will be your X train. And here we are just putting the polynomial transformation, poly features. And here we are putting a linear regression model. But we can also add as many modules as you want. So instead of repeating the same code every time, we can just construct this object and use it right away like this. Here we are just using my polynomial regression, okay, and we are directly train this object. Implicitly, when you do this model.fit, you're implicitly calling the object polynomial features and then take the result and give it to input as linear regression. So you see, it is way more compact, and you should do it because it simplifies a lot your life. And also to predict, the same thing happens. So pipelines are very good to keep the code readable, easy to understand, and to save you a lot of time in typing code. So let's now try to find, as I explained in the slides, the right polynomial degree p by using cross-validation. So here we are saying that we want to try this specific parameter, that is polynomial features degree. And we want to try all the degrees from 1 to 30. Okay, first we divide our we will use cross-validation, so we will have to divide our training set in 5 folds in this case. And we use again negative mean square error as scoring function, as we did last time. And now we fit this grid search. Observe that we are just using the training set here, okay? So actually what we are doing is here we are just doing grid search on this. Okay. Okay, the grid search is done automatically by this Python function. At the end, we will have just the results, that is the cross-validation error for each polynomial degree p. And we can just take the best parameter. It is saying that the best parameter is degree 2. And we can also get the best score, that is the opposite of the mean square error. So if we compute the root mean square error, this is the result. So this is the cross-validation error computed on the training set. We can get the best model, that is the one with p equal 2, and now we can train this model on the entire data set. So we are now training the model on this entire data set. And then we compute the error on the test set. And this is what we get. Let's get back to the slides to recap what we have seen in the code. So we have seen that we have played with the parameter that is p, the polynomial degree. And we have seen that the more we increase the p, the more our model becomes flexible, because it increases the number of parameters. If p is equal to 1, the model is theta 0 plus theta 1 x1. If p is equal to 2, the model is theta 0 plus theta 1 x1 plus theta 1 x2, x1 squared, etc., etc. So the number of parameters is 1, 2, 3. If p is equal to 2, if p is equal to 100, we have a lot of parameters. Okay, so and the more parameters, the more our model is able to twist. And we also observe that the more the p, the more the training error decreases, because again our line is able to adapt to each and any training point, training sample. We also observed that when p was equal to 1, we had a high test error, while if p was equal to 2, the test error was a bit smaller, which is good. But then, if we increased too much the p, the training error keeps decreasing, but the test error starts to increase. What it means? It means that the model is overfitting your data. It means that is adapting too much to the details of your training data, and it is not generalizing. It is not learning the important information in your data. So while it is performing very good in the training set, it starts to perform very bad in the test set. So you want to be in the middle between underfit and overfit. And so to be in the middle, you have just to take the model complexity, p in our case, and increase it little by little. And at the beginning, both test and error will decrease. It means that you're still underfitting. Then when you see that the test error starts to increase, then you have to stop, because otherwise you will overfit. Observe that when a model is overfitting, it also suffers high variance, because it is adapting too much to the details of your data. And so if you perturb your data a bit, the optimal parameters that you will get for your model completely change. So the model is very unstable. What we are talking about can also be summarized by this famous trade-off called bias versus variance trade-off, that tells you that if you want to reduce the bias, which is the error in the training set of your model, you are for sure also increase the variance of your model. So your model becomes more and more unstable. So we have seen already a way to avoid overfitting, to avoid your model starts to suffer too much variance, which is limiting the complexity, limiting the number of parameters. In this case is limiting p, the polynomial degree. There is another technique called regularization, which instead lets the model have many parameters, but tries to keep them small. This regularization is very simple. It just consists in modifying the loss function. Instead of just including the error with the dataset, we also add a regularization term which penalizes high values of the parameters. Okay, so observe here that when you compute the optimal parameters, which is the arg mean with respect to t theta of this loss function, you cannot minimize too much the error because you may have too high parameters, and so this regularization term would increase too much. So regularization prevents the model to go too close to your datasets and keeps a certain rigidity in your model, which avoids overfitting. So of course you will use the modified loss function only during training, while during test you will just use the error term, the mean square error in this case. So regularization is only useful in your during training to avoid overfitting, but then during test the error you will compute it always in the same way as before. Observe that in the extreme case where alpha is equal to 0, it means this term doesn't exist at all, and we are just performing ordinary linear regression. While if alpha is equal to infinite, or a very big number, when you minimize the loss function, you are just ignoring the first term, the error term. So at the end, you will force all the parameters to be 0, except the bias term theta 0. Observe in fact that into the regularization term, the bias is not included. So when this regularization coefficient alpha is very high, actually your model is completely rigid. It's like just a constant value. Okay? So it doesn't vary at all with the features. It remains constant. Now, alpha is a delicate parameter, is another hyperparameter that you have to choose. It shouldn't be too high, because otherwise you have a model that is too rigid and you underfit, but it shouldn't be too low, because otherwise you don't regularize at all and you again overfit. It should be the right value. Which one? Well, it depends on your dataset, so it's again a matter of trial and error, and you can use grid search and cross-validation to do so, and we will see how to do it in our code. The code for regularization is in this notebook, b.regularization, and here I just first start with the linear model. So I train it in the training set and I print the error on the test set. Then I use a regularized linear regression. In Python it is called ridge. Okay, so a regularized regression can also be called ridge regression. And this is the test error. So, and then I try different values of regularization coefficient, and I try all these values just in the training sets, and I use cross-validation to try these values. So at the end I plot the cross-validation error, and it seems that this value of alpha is the best. So I choose this value, and then I train again the model on the entire training set, and I then print the error on the test set. And okay, we improved with respect to before, where we didn't have any regularization. Then I do polynomial regression, first without regularization, and we see overfit. And notice that here we are doing polynomial regression with multiple features, not just one. Okay, so without any regularization, we are good in the training set, but we are bad in the test set. So we are worse than the linear model if you use the quadratic regression. So to avoid this, we can regularize our quadratic model, and we do so. And in particular, here with this code, I'm checking different values of regularization coefficient. Again, I do this just in the training set, and I plot the cross-validation error. It seems that this value of alpha is the best. So I fix this value, I train my regularized quadratic model on the training set with this fixed value of alpha, and then I plot the result, the error in the test set. And observe that this is the result when I do polynomial of degree 2 regression and ridge regularization. This is the result, so it's improved with respect to the other models. Now let's go back to the slides and let's talk about scaling. Scaling is an operation that you should almost always do before training any machine learning model. Let's see why it is important. This is how our dataset looks like. We have features with high values and features with small values. If you just train a simple regression model, this is not a problem, because the model looks something like that. So if your xj's are small for a certain feature j, it doesn't matter, because after you run ordinary least square, you will very likely have high values for the parameters theta j. So if the xj's are small, you will likely have high theta j's to compensate for them. But if you now had a regularization term, you are forcing all the parameters to be small. So if a certain variable, poor variable, is already small by itself, you are also forcing his theta j to be small as well. The result is that the contribution for that variable will completely disappear from the regression model. So you are cancelling out some features, and maybe those features are very relevant. Suppose, for instance, that you have features expressed in bytes and others expressed in kilobytes. If you regularize, you are likely to cancel out the features in bytes, in kilobytes, because they are smaller than the features in bytes. How to avoid this? The answer is scaling. Let's see directly the result of scaling. So scaling transforms your dataset from the left to the right. The transformed dataset has the following characteristics. First, all the values for all the features are more or less centered around 0. And then the scale of all the features is comparable. Mathematically, we can achieve this in two ways, or more ways, but the main ones are two: min-max scalar or standard scalar. Let's see min-max scalar, and let's scale feature j. First, you need to compute the mean of feature j across all samples. Then you compute the difference between the sample feature for each sample and the average. And then you normalize by the range that that feature can take. And so first observe that it's not important, after the transformation, it's not important the absolute value of the original feature, but just its variability around the mean. And also the transformed values are guaranteed to be between -1 and 1. Standard scalar is similar, but we normalize by the standard deviation. Observe that when you scale, you need to compute the mean, the max, the minimum, etc. And pay attention that you should compute them only looking at the training set, because the test set, you put it aside, you don't see it until the end of your project. So when you scale, you just have to take these metrics, mean, max, and minimum, from your training set only. I told you that scaling is important when you regularize, but even if you don't regularize, scaling is not mandatory maybe, but it's recommended anyways. So suppose you run an OLS, ordinary square, and you obtain a model like that. Okay, and suppose theta 1 is equal to 2 and theta 2 is equal to 5,000. Now, if we scaled our dataset before, we are sure that all the x are in the same scale. And so the contribution of the second feature is way higher than the contribution of the first feature. In other words, we are sure that feature 2 is more important than feature 1. So scaling also helps to increase the interpretability of the model, because just by looking at how big coefficients are, we can understand if a feature is more or less important. And this aspect is considered in a feature selection technique called recursive feature elimination. So in any feature selection technique, we are trying not to include all the features, but just to look for the right ones. And recursive feature elimination is a technique to automatically get a good feature subset. Let's see how it works. First, you have to scale your dataset using standard scaler. Then you train an ordinary least square with all the features. Then you look at the coefficients you get, and you take the features with the smallest coefficient, because this feature is the least important. You take the resulting model and you train it again, always on the training set. Again, you check the coefficients, and again you remove the feature with the smallest coefficients, because we assume it is the least important. And you repeat it again until you're left with n features, where n is up to you to decide. So at the beginning you have to decide if you want 3 features or 2 or 5. Okay, and we can also let an algorithm decide n for us, okay, by using this recursive feature elimination plus cross-validation. And actually it works just by repeating the recursive feature elimination with different values of n, and it suggests us the value of n that gave the smallest cross-validation error. So in this notebook here, b.regularization, you can check yourself how you can regularize your model, your polynomial regression model, and also at the end how you can apply recursive feature elimination, okay, with cross-validation. So I let you go through the notebook yourself. I put all the comments here for you to understand, but if you have any doubt, don't hesitate to write. So far we have seen one type of supervised learning, that is regression, in which the labels we want to infer are numbers. We will now talk instead of classification, in which the labels are categories, so their values are in a discrete set. We will start with the simple classification techniques called logistic regression. Pay attention that even if it's called logistic regression, it is actually a classification method. So we will use in our example the same dataset in which we want to infer resolutions. If you remember, up to now we have to infer resolutions, we have formalized the problem as a regression, because we have interpreted resolutions as numbers. We will now instead interpret these resolutions as categories. So a certain connection can be in the category 144p or 360p, etc., depending on the resolution of the video that the user was consuming in that connection. So this is to tell you that when you have a data science problem, sometimes you can choose if applying regression or classification. You are not obliged to use one or the other. So let's start with the simplest case of logistic regression, that is binary regression, binary logistic regression, which means we have just two classes that we call class 0 or class 1, negative or positive. For instance, we can just try to separate the low resolution videos from the high resolution videos. We can establish that after 720p, the video is considered high resolution. And so we have just two classes: less than 720p, low resolution, or higher. So in logistic regression, we do not predict directly the class of a sample. We instead predict the probability of a certain sample X to be positive, which is actually this. Okay, and we predict it with a certain parametric function h theta, where the parameters are theta, which is something like this. Here the sigma is the function called sigmoid, which has this shape here. So observe that the sigmoid goes from 0 to 1 and goes close to 1 for positive values and close to 0 for negative values. Okay, and so this function is perfect to use with logistic regression because it gives a number from 0 to 1, which is perfect to express probabilities. And we established that if this function h is more than 0.5, so if we are in this region here, we say that we classify the sample as positive. Okay, so the predicted class is 1. Otherwise, the predicted class is 0. Okay, so we can visually express logistic regression as a neural network composed by just one neuron. So just to understand what this representation means is that here we just have theta 0 multiplied by 1 plus theta 1 multiplied by x1 plus theta 2 multiplied by x2. Okay, this means that we are summing all these multiplications, and finally we apply a sigmoid. And what we have is our approximation function. When we train a logistic regression model, we actually try to find the best parameters here. And to do so, we need first to define a loss function and then to minimize it. In logistic regression, the log function is called log loss and is something like that. So the loss function on a single sample x, whose true class is y, is this one. If the true class is 1, the loss function is this value. If the true class is 0, the loss function is this other value. So to understand the logic behind it, suppose you have a sample x whose true class is 1. Okay, and suppose that your approximation function, that is this sigma of scalar product of theta multiplied by x, suppose that this is something like 1 or very close to 1, let's say 0.9. So for instance, you're here. So if you compute the logarithm of 0.999, for instance, the result is almost logarithm of 1, that is almost 0. So the loss function is actually 0 or close to 0. So in other words, when the true class of the label of the sample is 1, your model is forced to have an approximation that is close to 1 as well. Otherwise, if instead the approximation was something like here, for instance 0.01, this number is close to 0, and logarithm of this number is thus close to infinite, and thus the loss function in this case is minus infinite. Okay, so when we train a model with this expression of the loss function, we are forcing our approximation function to be close to 1 for all the samples whose true class is 1. And we are reasoning it the same way. We can understand that we are also forcing the approximation function of the negative classes to be close to 0 as well. This is to minimize the loss function. So this is intuitively what the model should do to take the loss function low. Of course, we need a mathematical method to achieve this, and fortunately this loss function is a derivable function and also convex. So this is derivable, so we can compute the gradient of the loss function with respect to theta. So I will write the gradient here. The gradient is the derivative of the loss function with respect to theta 0, then the derivative of the loss function with respect to theta 1, etc., etc. So since you can show that this loss function is derivable, this gradient exists. Also, this loss function is convex, so it looks something like this. So there is a minimum, and this minimum is unique, and you can show that thanks to this convexity, a method called gradient descent will for sure give you the minimum of the loss function. Let's see how the gradient descent works. So, gradient descent is an iterative procedure in which you start by initializing your parameter vector with any value, whatever. And then you compute every time the gradient of the loss function using the parameters you have so far, and you update the parameter using this expression. Okay, you perturb every time the parameters. So you obtain a new vector of parameters. So you can recompute the gradient with this new set of parameters and update again the vector of parameters. At the end, you will converge to a value of theta, which is actually the optimal one, meaning that it is actually the minimum of the loss function. So graphically, what we are doing by applying gradient descent is that we start by whatever value of theta. Suppose this is theta 1, theta 2, and the vertical axis is the loss function with respect to theta, x and y. So what we are doing here is that every time we go to the opposite direction of the gradient, and so we start from a certain value of theta and then we update it and we go to another value of theta, then we descend again, modifying the value of theta. And by doing this repeatedly, thanks to convexity, we can show that we arrive to the minimum. At this minimum, the gradient is 0. And so when we arrive there, we actually converge, meaning that the updates are always 0, so we don't move from there. So in logistic regression, we are sure that by applying simply gradient descent, we can easily get this optimal parameter, which minimizes the log loss. I will skip the mathematics. What I just want to show you is that if we compute the loss function on the entire dataset, this is just the average of the loss function on any single sample. And if we compute and so for the gradient is the same. So the gradient of the loss function on the entire dataset is the average of the gradient of the loss function on each single sample. And if we compute the gradient on each sample, you will see mathematically, you can skip it, but you can easily see it, that the result is nice. The expression of the gradients of the loss function on a single sample is just the multiplication of the residual by the sample itself. So it's very easy to compute this gradient. And thus it's very easy to perform gradient descent. Now, you have different strategies to perform gradient descent. The simplest one, conceptually at least, is the full gradient descent, meaning that every time you compute the entire gradient of the loss function and you update the parameter vector with this value. The problem is that to compute the gradient, you need to compute the gradient of the loss function at each sample. So you need to travel across the entire dataset before updating your parameters. If your dataset is too big, this can be too time-consuming. So another way of making gradient descent is stochastic gradient descent, in which you just compute the gradient. You take a random sample and you compute the gradient of the loss function just on that sample, and you immediately update the parameters. So you, instead of waiting to travel the entire dataset to update the parameter, you do it for every sample you evaluate. So this method is sometimes more convenient. Another method is batch gradient descent, in which you take a subset of samples instead of just one, and you update the parameter after you evaluate this subset of samples. It can be 30, 60 samples, for instance. No matter which method you use, we define an epoch of training when we have traveled the entire dataset. When we use full gradient descent, we update the parameter once for each epoch, while if we do stochastic gradient descent, for each epoch we update the parameter vector many times, once per each sample in fact. We now show that logistic regression is a linear classifier. Let's see what it means. So we have said that we classify a sample as 1 if and only if the approximation function is more than 0.5. But the approximation function is nothing else than a sigmoid, okay? And the sigmoid is higher than 0.5 for all the positive numbers. So in other words, we classify a sample X as class 1 if theta times X is positive. So if we now represent our plane and the two features x1 and x2, we can draw a straight line whose equation is theta times x, theta transpose times x equal to 0. This is the equation of this line. And we see that on the one side of the line, we classify all the samples as positive. And on the other side, we classify all the samples as negative. Now, this line here is called decision boundary. Decision boundary. And since this decision boundary is expressed by a linear equation, we say that the classifier is a linear classifier. We will see later in this course non-linear classifiers that are able to distinguish classes like, for example, this. Okay? So these non-linear classifiers are able to say that within this curve, they will classify all the samples within this curve as positive and outside as negative. Okay, and you see that the decision boundary is not linear. Okay, this is why these classifiers are defined as non-linear classifiers. Now, a logistic regression classifier is not capable of doing this, but is, let's say, simpler. It can only draw decision boundaries that are linear. So it can perform very simple classification tasks, not complex as this one. Now we have just drawn examples in 2 dimensions, but the reasoning is the same in higher dimensions. In this case, we don't talk, the decision boundaries are not lines, but they are hyperplanes. Now, so far we have talked about binary logistic regression, but we can also do multi-class classification with logistic regression, and in this case we talk about multinomial logistic regression. So suppose you have 3 classes, 1, 2, 3. Now, instead of just 1 neuron, we need 3 neurons, 1 per each class, and each neuron has its parameters, theta 1, theta 2, and theta 3. To get the predicted class of a sample, we take a sample vector and we multiply it by the parameter vector of the first neuron, and we obtain S1. Okay, this is S1, for example. We do the same to obtain S2 and to obtain S3. These numbers are called scores, and they can be positive, negative, very big, very small, etc. But at the end, we would like to have something that looks like a probability. This is why we add a softmax layer. A softmax of class K, for example, X, is something like that. So it's the exponential of the score of class K. Suppose we are looking at class 2 is the exponential of S2 normalized by the sum of the exponential of all the other classes. Like this, we are sure that this pk hat is a number between 0 and 1, and that the sum of p1, p2, and p3 is always 1. So we can actually consider this p as probabilities. So every time a sample comes, we can compute, for instance, probabilities like 0.8, 0.15, and 0.05. So in this case, this sample has, let's say, more probability to be of class 1. So we will classify it as class 1. So the final class of each sample is just the class with the highest probability. In order to train our multinomial logistic regression, we have to find the best parameters here, theta 1, theta 2, theta 3, etc. To do so, we first need to define a loss function, as usual, and then we need to minimize the loss function. In case of multinomial logistic regression, the loss function is called cross entropy, and it looks something like that. This is the loss function on a certain sample xi. this loss function depends on this predicted probability p hat. This is the predicted probability of sample I of being of class ki, where ki is the true class. Observe that the predicted probability is the thing that we computed before passing through the softmax, and which of course depends on these weights here. So in order to minimize this loss function, we need to have this probability as high as possible, because if this p is high, the logarithm of the p is high, and thus the minus logarithm of p is very low, so we are actually minimizing the loss. In other words, by minimizing the loss, we are forcing the model to predict with a very high probability the true class ki of each sample I. You can skip this part, but here I want just to say that we first talked about binary logistic regression, then multinomial logistic regression. Actually, if you run a multinomial logistic regression with just two classes, it is exactly equivalent to a binary logistic regression. I think you shouldn't be surprised of this. So now let's go to the code to see how to run logistic regression in practice. The code to run logistic regression is in GitHub, and the name is c.classification. You can run it yourself. I will just go through it very fast. So first, I just run a binary classification. So I just established two classes, high resolution, that are the videos above 720p, and low resolution, all the others. And I run a binary logistic regression. What I want to show you is that you train, of course, the model on the training set, and at the end you have your model, and you have two functions. You have predict proba, which gives you the probability for each sample of the test set to be of class 0 or to be of class 1. And of course their sum is always 1. And then you also have predict, that actually gives you the class that you predict, either 0 or 1. And of course the class is the maximum between the first probability or the second probability. Here we are comparing the true class with the predicted class. Another thing I want to show you is that by default logistic regression in scikit-learn library performs regularization. So at the beginning I didn't want to perform any regularization, so I set the regularization coefficient to close to 0. So if you put here 0, it will give you an error. So you have to put a number that is practically 0, 1, 10 to the power of minus 9 in my case. But it's always a good idea to regularize. So then it's good to try different values of regularization factors. And I do this by performing a grid search at the end of this notebook. You can check it yourself. Again, now I talk of scaling. Scaling is very important with logistic regression, because every time you have a sigmoid, and in logistic regression we use a sigmoid, then it is better to scale your dataset, because if your dataset is the features are very high, then your sigmoid can just take the value 0 or 1. So the sigmoid is sensible to the scale of the features, and it is safer to always scale the dataset whenever you use a method which implies sigmoids. Logistic regression and also neural networks, as we will see. So here I'm just first normalizing through a standard scaler, and then I run again a logistic regression on the normalized test sets, and I verified that actually performance improves. Here I just show the decision boundary, and here I perform multinomial logistic regression. Here I want to spend a bit more time. In this case I create three categories. All the videos that are above 240p, I consider them low resolution. The other videos are mid resolution. If they are more than 480p, they are considered high resolution. And here I create a pipeline in which first I give the scalar and then the logistic regression. This time it is a multinomial regression, and that's all. For the rest, I run the model in the same way. So I first train, then I predict on the test set, and I check the accuracy. The accuracy is the fraction of times that the predicted class is equal to the true class. And observe that in this model the accuracy is quite high. So we could say, okay, the accuracy is high, so the model is good. This is completely wrong, and I invite you not to say this and to pay more attention. Why? Because let's look into our results more closely. Here I'm plotting through this function the confusion matrix. In the confusion matrix we have the true labels and the predicted labels. This one here means that we correctly classified the class 2 samples 100% of times. So this is good. But if we consider class 0, we classified always 100% of times the class 0 samples as class 2. So for class 0 we were wrong 100% of the times. And also for class 1 our classification was very bad, because we classified class 1 samples as correctly only 20% of times, because for the rest we classified them as class 2. So the important metric to look at when you do classification is the confusion matrix, not just the accuracy score. And actually, to have a good confusion matrix, you would like to have the diagonals as close to 1 as possible. And here, of course, we are very far from these results. Why we have a so bad classifier? Because in our dataset we suffer class imbalance. What does it mean? It means that there is one class that is prevalent and that counts most of the samples. In this case, class 2 has 210 examples in the training set, while the other classes are smaller, they have few samples. So when we train our logistic regression, the algorithm for training is just trying to minimize the loss function. And of course, it will prefer to minimize the loss function for the class 2, because it concurs the most to the total loss function, while the other classes are almost negligible. Their contribution to the loss function is almost negligible because they are just few samples. So we end up with a bad classifier, and that's normal. How can we solve this problem? We can solve it by using rebalancing methods. So we want to obtain, before training a model, a balanced dataset. How can we do it? A method that is very simple and intuitive is called synthetic minority oversampling technique, who has now 10,000 citations, even if it's very simple conceptually. What we do here is that we take the smaller classes and we amplify them. In other words, we just generate new samples, synthetic samples, in these small classes. How do we invent these samples? Well, we use a technique called key nearest neighbor to generate samples, new samples that look like the real samples that are in these small classes. So here I have the original training set, and I am applying smooth to obtain a balanced training set. And now I just train my model on the balanced training set. At the end, I measure the performance of the model on the test set. And I have now a much better confusion matrix. Okay, so now the diagonals are a bit better. Of course, we are a bit worse in predicting the prevalent class, but in general we are better. So of course we can still improve this classification, but still solving the class imbalance problem helped us in having a better classifier. A nice way to summarize the performance of a classifier on the test set, of course, is the classification report. Let's see the slide for that. Is the last slide, I think. Yes. So let's see directly what these numbers mean. Let's consider, for example, class 0. So precision 0.29 means that 29% of samples classified as 0 are actually 0. And recall 0.75 means that 70% of class 0 samples are correctly classified. Then we have F1 score, that is a combination of precision and recall. The accuracy is the overall error rate, so is the percentage of times that our classified class was equal to the actual class. And then we have the support, that is just the number of samples of each class. We will see again these numbers in more detail when we will do anomaly detection. In classification they are nice as well to check, but again I repeat, the best way to check the performance of a classifier is to visualize the confusion matrix on the test set. That's all for this lesson. Let's recap what we have seen. So we have continued regression. In particular, we implemented polynomial regression, and we have encountered a fundamental trade-off of machine learning: variance versus bias. We understood that the more complex is your model, the less is the bias, but the more is the variance that your model suffers. It means that it risks to overfit your dataset. In order to avoid this, either you limit the complexity of your model, in our case we limit the degree of our polynomial, or we use regularization techniques. We also understood the importance of scaling the dataset before training any model, and a method to find the most important feature when we want to have a parsimonious model. Then we started to talk about classification, and in particular logistic regression. We understood that the best performance indicator is not really the accuracy, but the confusion matrix. And we also saw how to solve the class imbalance problem that is very frequent in data science projects. In next lesson, we will finally see neural networks.